We have three types of cycles. Among them is Otto cycle, diesel cycle, and dual cycle. Dual cycle is the combination of Otto cycle and diesel cycle. Now we learn about the derivation of Otto cycle. Okay. Otto cycle. Otto cycle is also known as constant volume cycle. Now we see the PV diagram of Otto cycle. Let P coming to the first process 1 to 2 isentropic constant process. It means isentropic is constant. And coming to the 2 to 3 process, constant volume process. 2 to 3 is a constant volume process. It means there is no change in volume at this process 2 to 3. Now coming to the 3 to 4 process, it is also constant isotopic process. Therefore, and again 4 to 1 process is also constant volume process. That is, the engine is in first condition. Coming to that, now we see the TS diagram of Otto cycle. TS diagram of Otto cycle. Same like this, but oppositely. Quite opposite to this. 1, 2. So what do we like this? Observe these two. 2 to 3 processes. 2 to 3 process constant volume process. But here 1 to 2 constant isotropic process. Here 2 to 3, 1 to 2 is equal, and 3 to 4 here also. 3 to 4 is isentropic is constant, and here 3 to 4 is isentropic is constant. That's we are representing this. It is here. Clearly coming to the processes one by one. That is 1 to 2 process is constant isentropic compression. That is isentropic compression. That is 1 to 2 is compression process. That is, in engine 1 to 2 process is the compression process. It means we have 4 processes. That is 1 to 2, 2 to 3, 3 to 4, 4 to 1. 1 to 2 is constant isentropic process. 2 to 3 is constant volume process. That is, during I will show you that clearly. That coming to this clearly, Otto cycle. Isentropic compression, that is, the piston moves from BDC, bottom dead center, to TDC, top dead center, and it is 1 to 2 process. That it is 1 to 2 process. Now 1 to 2 process. 1 to 2 process is BDC, piston moves from BDC to TDC, and 2 to 3 process. 2 to 3 process constant volume process. That is constant volume heat addition. This is the process 2 to 3 constant volume heat addition process. Therefore, the piston moves from BDC. The piston moves from, and coming to the process 2 to 3 at a constant volume heat addition takes place. It is here heat addition takes place. Now coming to this, at a constant volume, here the volume is constant and the heat is added to the engine, and that is 2 to 3 process at a constant volume heat is added. And coming to the 3 to 4 process, that is here 3 to 4 process is isentropic expansion. That is isentropic is constant. And coming to this 3 to 4 process, that is due to the addition of heat, piston moves from top dead center to bottom dead center. That is, the energy in this process, the expansion will take place. That is, this process is called, this process is also called the use the energy. In total of the 4 revolutions, in 4 process, only this process will use the energy from the engine to the wheels, or it may be work. And coming to the process 4 to 1, that is, at constant volume, these gases will burn due to this heat addition and expansion. The gases which are present at the cylinder during this photo 1 process, heat rejection takes place. That is heat the heat presence in the burned gases will go out. That is heat rejection takes place in photo 1 process. The main consideration is compression ratio. In the engine, compression ratio will decide the efficiency of the engine. If the compression ratio is more, then the efficiency of the engine will increases, and if the compression ratio is less, then the efficiency of the engine when compared to the compression ratio which is have higher compression ratio is less efficiency than that. Therefore, compression ratio is actually given by volume at maximum by volume at minimum. Volume at maximum means V1, where this is the V1 volume, that is the volume of the cylinder, and V2 the clearance volume. Clearance volume is the distance between the cylinder, distance between the top most end of the cylinder and the piston when it is at top dead center. Clearly that volume of cylinder by clearance volume, that is the compression ratio, which is the most important useful that declares the efficiency of a engine particularly. Coming to the process 1 to 2, our main aim is to derive a efficiency and the mean effective pressure of Otto cycle. Therefore, coming to the process, each process one by one, and 1 to 2 process isentropic compression process, that is the relation between pressure and volume in isentropic process, that is isentropic compression process. PV for gamma is equals to constant, and relation between temperature and the volume in this process, isentropic process, is TV for gamma minus 1 equals to constant, and using this process, pressure or temperature will be find out during 1 to 2 process. And now we have to find out using this relation. T2 by T1 is relation. T2 by T1 is equals to V2 by V1 whole power gamma minus 1. It is clearly that T2 by T1 is equals to V1 by V2 whole power gamma minus 1. And coming to this, clearly T2 is equals to T1 RC. Here RC means V1 by V2. Here clearly that RC V1 by V2. V1, that is clearly that V1 by V2. V total volume of cylinder, and V2 so volume, so not swept volume, it is a clearance volume, it is a total volume. V1 is the total volume of cylinder, and V2 is the clearance volume. That is clearly T2 is equals to T1 RC power gamma minus 1. Here RC equals to V1 by V2, that is RC equals to whole power gamma minus 1. RC means compression ratio. Now coming to the process 2 to 3, that is constant volume at heat addition, that is 2 to 3 constant volume, that is V3 equals to V2. Since it is a constant volume process, V2 equals to V3. Therefore, we know that this form PV by T is equals to constant, pressure into volume by T is equals to constant. That is clearly that heat addition, we know the formula mCV dt. Heat addition or heat reduction, the expression for the heat is mCV into dt, that is m is considered as 1 gram or kgs, whatever it may be, Cv into T3 minus T2, that is specific constant volume, and dt means T3 minus T2. Since it is a 2 to 3 process, maximum temperature T3 minus T2, since it is a maximum temperature. This is constant volume at heat addition. V2 is equals to V3. Since V2 equals to V3, here is the addition. Here is the constant heat addition 2 to 3 process. In 2 to 3 process, heat addition takes place. Therefore, Q heat addition Q in is equals to Cv into T3 minus T2. And coming to the process 2 to 4, that is clearly that 3 to 4 process. Yeah. Coming to the process 3 to 4, isentropic expansion process. This is the piston moves from top dead center to bottom dead center. That is, here the temperature decreases, the pressure decrease takes place. Clearly observe this arc. Therefore, 3 to 4 is a process isentropic expansion. Here is also compression ratio. Compression ratio means we know that V1 by V2. Clearly that V1 is equals to V4. Here see clearly V1 equals to V4, V2 equals to V3. Therefore, V2 by V1 equals to V4 by V3. And using the same form, where we have used in first process isentropic process. Only use this isentropic. Here also isentropic. Just use the same form and used to derive T3 by T4 and V4 by V3 whole power gamma minus 1 is equals to V2 by V4 by V3 is equals to RC. Therefore RC whole power gamma minus 1. Therefore we know the expression for T3 in terms of T4 and RC. Clearly here also that it is equals to T1 temperature of T2 at the point top dead center. The temperature is at in terms T1 and RC whole power gamma minus 1. Therefore coming to the process, 4 to 1 process, constant volume heat rejection process. Here is also P4 equals to V1. Clearly we know that. Therefore Q out. Therefore here heat rejection takes place at the constant volume. Therefore MCV T4 minus T1. Now here the constant volume is not, but it is ideal. We are making it as a reference in what we are using in real life. Therefore these are ideal cycle. Therefore at constant volume means it will be ideal cycle. Therefore that is Cv into T4 minus T1. Here is 4 is the highest temperature, therefore my 4 minus lowest temperature point, that is equals to T1. Here also we can use that since it is a constant volume process, P by T is equals to constant. Here P by T is equals to constant. Clearly here also, since it is a constant volume process, P by T is equals to constant. That is we can use here directly proportional. P is directly proportional to T. Therefore P4 by T1 is equals to T4 by T1. By using this we can also define the pressure and the pressure in this process. See clearly same here also. Since it is a 2 to 3 process, therefore P2 by P1 is equals to 2 to 3 process. P2 by P3 equals to P2 by T3. Since they are directly proportional. The main theme of the Otto cycle derivation is last and the but one is the two main steps are efficiency and the mean effective pressure. Now that the 4 steps we have solved before used to derive the efficiency of Otto cycle. Therefore efficiency means output by input, that is output is the work done, net work done, and the heat input is the Q heat input, that is heat added, and work done is given by heat input minus Q out, that is heat added minus heat outlet by heat input. Therefore clearly that 1 minus Q out by Q in. Therefore 1 minus Cv T4 minus T1. We know we derived that. Here see clearly that Q. Here clearly derive that Q out. See clearly Q out Cv T4 minus T1 and Q in Cv T3 minus T2. Therefore we substitute clearly here Cv cancels and T4 minus T1 T3 minus T2, and observe before the process 2 and processes 1 and 2 1 and 3 process substitute T3 and T2 here. Therefore this cancels and will clearly will become 1 minus 1 by R power gamma minus 1. Efficiency of a Otto cycle depends only upon the properties, that is compression ratio and the gamma of a value.